this is the lone problem which can exactly be solved, and the solution that we obtain for the problem of hydrogen atom, it certainly verifies the validity of quantum mechanics itself. That's why it acts as a basis, as a basic fundamental cornerstone for the field of quantum mechanics. And being simple, having a dipolic nature where you have a proton and electron, and choosing the simplest spherical symmetry in resolving this problem leads us to the results. And these results that we obtain, they purely replace the Bohr predictions, the Bohr model of hydrogen atom, which accurately predicts the existence of spectral lines in hydrogen atom. And the argument that's given by the Bohr is that you have electron, they are rolling in the shells, and he calls these shells as non-radiating shells. So these are the regions around the nucleus of the hydrogen atom where electron does not lose energy on its own. Now, the Bohr model is purely replaced by the Schrödinger version of quantum mechanics, where we naturally achieve these quantization rules which acted as postulates in Bohr's model of hydrogen atom. So quantum, I should call it a testing laboratory as the hydrogen atom investigated by launching Schrödinger's equation in spherical polar coordinates to solve the problem of hydrogen atom. So it becomes a basis of all the advanced quantum mechanics that we have for the complex systems like many electron atoms or even molecules, and sufficing the fact that the quantum mechanics works, and it works in a very, very simplistic atom in the nature, which is called as hydrogen atom. Now, the point is basically that what I'm trying to do here is to realize the main important results of solving the problem of hydrogen atom. Now, you can see here that what we have, we will be discussing the results that we obtain solving the problem of hydrogen atom, and how we solve it, we understand that, and that will be attached to this video, the complete solution of Schrödinger's wave equation. So what am I trying to do here is, before we go to the pure mathematical structure, which I have already uploaded as a lecture on YouTube, this part will act as the introduction of that problem, so that one has exactly in mind what he's going to do, and what are the results that we obtain by solving the problem of hydrogen atom. Now the point is that that here we are using the Schrödinger's equation, and probably I should call Schrödinger's time-independent equation. So what we have here, hydrogen is the simplest of all atoms. It consists of one proton and one electron, and solving Schrödinger's equation for hydrogen, what it reveals its quantized energy states. And these quantized energy states were also postulated by Niels Bohr. But here, we naturally obtain the quantization rules by applying the boundary conditions when we solve the problem of Schrödinger's wave equation using a variable separable approach and assuming the pure spherical symmetry of the problem. So this is the point. So these solutions are crucial for understanding the atomic physics, and certainly they become the basis for the other branches of the physics, like molecular physics, condensed matter physics, and even in nuclear physics. So what we have the time-independent Schrödinger's equation that's written down here, and this equation we have to write in terms of the spherical polar coordinates. So this is our Schrödinger's equation, and what we do, we solve this Schrödinger's wave equation. We write down this equation in spherical polar coordinates. Then what we do is we use the variable separable approach to solve this problem, because there are three unknowns in this equation. We cannot directly solve this problem. So for that, what we do is we use variable separable approach, and then we introduce some of the constants in solving those separated parts of that equation. And the constants that we introduce, they are a result of the boundary conditions of the given problem. So what we do, we solve it in spherical polar coordinates because of the Coulomb potential. Because Coulomb potential has the dependence on R, it has the dependence on the radius in the Schrödinger's equation. You can see here, this part is enclosed by R. So what we can also solve this problem using Cartesian coordinates, but solving this problem in Cartesian coordinates will take longer, and it will be very, very complicated calculations will be involved to solve it. So what we do, we use separation of variables. You will see in this video that how we approach this separation of variables in sorting out the boundary conditions. So what we do, we separate the wave function into radial part, into the polar part, and the azimuthal part. R, theta, and phi, we come up with three equations independent of each other. And these three equations come into existence by introducing those boundary conditions, by introducing those constants in the equations. And this leads us to the quantum numbers. Naturally, n is the principal quantum number, L is the azimuthal quantum number, and m is the magnetic quantum number. So what we have these three quantum numbers, which we naturally come across while solving the Schrödinger's equation for hydrogen atom using variable separable approach. So n is your principal quantum number. It tells you about the energy levels. You have the energy levels of the hydrogen atom. The electron can be present in those energy levels. And then you have, the next is L, this is called azimuthal quantum number. It's also called as orbital quantum number, and it gives us the measure of the orbital angular momentum of the electron. And then we have the magnetic quantum number, which is given by m, and generally it's written as ml. It tells us about the orientation of angular momentum. So what we have here, what we find by what we will see at the end of this video, we are going to see that the energy that you have linked with the electron in the hydrogen atom, it does not depend on orbital angular momentum, it does not depend on magnetic quantum number. What it depends on is the principal quantum number. It depends on the values of m. And you can see in this graph how the energy is written in the form of the results that you obtain by solving Schrödinger's equation. So you have these dots reflecting the value of energy as you move from n equal to 1, because n is an integral number. It cannot equal to 0. So it has to start with 1. So you have a point for 1, point for 2, point for 3, 4, and 5. So you can see as you move away, the value of the energy between the two states, it goes on decreasing. And I should say at this point of time that if you take your system to the higher quantum numbers, if you take it to the higher principal quantum numbers, it will automatically connect you. It will automatically connect you to the classical results. So now what we have now for a given n, you will find there will be multiple azimuthal quantum numbers, and there will be multiple magnetic quantum numbers. So what does that mean? This gives birth to a well-known term in quantum mechanics, what's called as degeneracy. So this degeneracy explains why different orbital shapes can have the same energy. I mean, you have different orbitals, S, P, D, F, and within an orbital, say, taking an example of p orbital, px, py, and pz, they happen to have different orientations in space, but they have the same energy, right? So having the same energy tells us about the degeneracy of these energy states. Now, another important part that we will obtain is the radial wave function, because solving the Schrödinger's equation will lead us to the radial wave function, and radial wave function it will give us the probability distribution, and the radial probability distribution shows where the electron is likely to be found in the hydrogen atom at the different values of n. So here you can see a simple graph has been plotted between the radial probability and the radius of hydrogen atom. And you can see the peaks for the different values. And the peak is reflecting the maximum probability of finding the electron in hydrogen atom, depending on the principal quantum number. So for the different values of the data that you have here, you find those peaks in the probabilities. Because here you are doing quantum mechanics. When you do quantum mechanics, you are dealing with the probabilities of finding the electron. The electron is not behaving as a point mass. It is behaving as a cloud where the probability of finding the electron is going to be maximum. So what we have angular wave functions that we will obtain, and angular part is described by the spherical harmonics. As we know, we will later know in the video how to calculate those spherical harmonics, and they define the orbital shapes. Now these shapes are a calculation. They are a calculation based on using a different range of values for the particular problem, and resulting us to have the shapes of these orbitals like spherically symmetric shape like s orbital, p orbital, and d orbital. And then when you calculate the probability density, you take the square of the radial wave function. What you will obtain? You will obtain the probability of finding the electron, the maximum probability that you can have to find the electron. And what it leads us, the probability density leads us to the electron cloud region instead of the point mass in the region. So you don't have a point position, you don't have trajectories in quantum mechanics. In quantum mechanics, you only deal with the probabilities. So, to physically interpret it, electron is a probability cloud now. It's a probability cloud, not a point particle in the orbit. So it's a cloud of probabilities, where you have the regions of minimum probability, where you have the regions of maximum probabilities. As I said, if I take these n states, they resemble the Bohr orbits. If I take the value of this principal quantum number, very, very large. So another important result that we have is the transition between the levels. So there can be an absorption or the emission of the photons. And absorption can lead us a transition from one energy state to another energy state. And the emission can lead us an electron in already a higher energy state, it will bring it back to the ground state. So these are what we call as transitions. So Balmer series in visible spectrum matches the predictions. They match the predictions of solving the problem of hydrogen atom using Schrodinger's wave equation. And what we have here, we have fine structure. Now, what's the fine structure? If you have a line, a spectral line that is predicted by solving the problem of hydrogen atom, if you closely look at this line is further split into a couple of lines. So depending on the level that you have been trying to talk about. So hydrogen atom problem, which is pure in its nature, does not reflect its predictions when we check out those spectral lines using microscopes. So here what we do is we include certain corrections to the problem of hydrogen atom. And one is the relativistic correction, because electron is revolving around the nucleus, and the speed of the electron is very, it's somehow not very close to the speed of the light, but the speed is very large. So the speed, when you have more speed, you have to incorporate the relativistic corrections. And these relativistic corrections can explain us the fine structure of hydrogen atom. Now, in addition to the relativistic corrections, you have the spin-orbit coupling. So there is a coupling going on between the spin and the orbital motion of the electron. So resulting in the tiny energy splitting. This energy splitting is something that's reflected in the fine structure of hydrogen atom. It has importance in physics. It seems to be the basic fundamental theoretical laboratory experiment that's executed on this simplex atom, hydrogen, and giving us the results exactly solving the problem of hydrogen atom and confirming the validity of the quantum mechanics. So that's why hydrogen atom problem becomes the basic bone of the quantum mechanics, because quantum mechanics purely works in explaining the important arguments about the hydrogen atom. So hydrogen atom solution verifies this quantum mechanics predictions and forms the basis for complex atomic models that are ahead of us. So to conclude this discussion on the results of the hydrogen atom, what we have Schrodinger's equation, and it exactly describes the hydrogen atom. This is the beauty of this problem. And the next thing is that it explains the spectral lines, it explains the shapes of the orbitals and the probabilistic nature of electrons. It tells us that why you can have the maximum probability to find an electron and why you will have a minimum probability to find the electron. So this is how it makes the hydrogen atom problem a very, very important problem to be understood. So if you really want to understand quantum mechanics, the best thing is to start with the problem of hydrogen atom, apart from the syntax of quantum mechanics, because the set of rules that we have here, we have our own set of rules in quantum mechanics that are utilized to describe the quantum mechanical formalism.